Hey everyone, I wanted to take a few minutes to go over the density cubes activity. This is your second teach that you will do for your enrichment or your math classes or science classes, whatever you're assigned to for your field experience. This is the slide set, and I will share this with you in Canvas. Remember, you can always go here and click File, make a copy, entire presentation, and you can save a copy to your own drive, and you can customize this if you feel like you have a better um, engagement question or something that you want to include or something that you feel like as you read through here that you need to clarify better, you can add slides and customize this to make it your own. This is just set up so that you don't have to if you don't want to. So this is that first slide, density cubes activity. I would have this displayed on the board when students were coming into class. This has our data sheet for this activity, and I'll reference that. Let me see if I can drag this little black bar. I'll reference the data sheet. These will be printed in your student set that you bring home. When you come to class, I'll give you like a set of those sheets already printed. You'll also have a set of cubes, density cubes. Typically, I try to give you one set of cubes for each set of 10 students you have. So if you have 20 kids, I'll give you two sets. If you have like 23 or 24, I'll probably still give you two sets and you'll just have multiple sets of three or multiple groups of three. And then if you have closer to 30, I'll give you three sets. You'll also be assigned scales. This is the large scale that we have. These are roughly $140, $150. So if you wind up with these scales, please make sure you take really good care of them. I have ordered more scales that are smaller and more compact for y'all to transport more easily. Hopefully they'll be in early April. So anyways, let's move into the question. You could start with this on the screen if you'd rather, because this really gets their attention. So it says, why does a huge steel ship float while a tiny steel nail sinks? And I added some extra notes down here that you can reference. I wouldn't pull this up for kids, but you can reference it ahead of time when you're practicing. It says students often say bricks. So this was actually a different question. So let me add here additional optional engagement question. What weighs more, 1 pound of bricks or 1 pound of feathers? So this is another one you could consider. And so the follow-up would be students often say bricks because they seem denser or they weigh more per brick compared to per feather, even though mass is the same. This gets them thinking about material properties versus size versus mass. You could also say if they weigh the same, why do they seem so different? And so it gets your students thinking more about like the volume of the object. Even with like a steel ship and a tiny steel nail, the volume is two totally different things. The weight is two totally different things. And then how those two variables, interact to create the density, that obviously affects how it's going to float. So you would have maybe like a 3 to 5 minute conversation about this. Let them brainstorm some. This is not when you're revealing everything for the lesson. You're not completely explaining why the ship floats and the nail sinks or anything like that. You're just giving them an opportunity to express their thoughts and to kind of brainstorm, hear other people's thinking, and really just get excited about what they're about to learn about. All right, this is our next slide. So it says task one, using the data sheet provided, work with your partner to predict which materials will have the least mass to the greatest mass. Organize them on the provided table. So I go over this a lot in class, but just to reiterate, remember, it's so important for you to have like an extra sheet of paper to show them. And I would go around and say, okay, point at what table we're using when we're doing this part. And so they would point at the table and you go and you look at it. You may even want to say like, okay, acrylic, have y'all ever heard of any of these? And some people would say like, oh, PVC, I think that's like pipe. Some of them may not know that, some may not. Or they may say pine, that's a type of wood, or copper, that's orangey or something. So you can give them a few, maybe 30 seconds to a minute to just talk a little bit. And then you would say like, okay, so on your own, or you could have them do it in partner pairs, whatever you choose. I want you to label these 1 through 10, one being the one that you think is the least mass, the lowest mass, and then 10 the greatest. And so then they'll write this on there. This is not necessarily relevant for the activity. This is just a way for your middle schoolers, you could say, if you're competitive at the end of the lesson, we'll compare and see like who is accurate on their predictions. So it gets them involved in making predictions, thinking about like why would something be a lower mass, a greater mass, but it's not really the end game of this activity. So don't spend a whole bunch of time here. Next slide is task two, starting at your assigned station. And so we talked about this in class. I suggest having 5 stations per set of density cubes. So each set of density cubes has 10 cubes. And if you have 5 stations, you would have 2 cubes at each station. Depending on when my little small scales come in, I'll assign you scales. You most likely will not be able to have one scale for every 2 cubes. So if you're able, I would say maybe like 2 cubes on this side of the table, 2 cubes on the other side, and those 2 stations are sharing a scale in the middle. All right, so that's another option. But anyways, I would have 5 stations per set of density cubes. What that means, if you have 30 kids, you're going to have 3 sets of 5. So they're rotating within their little set of 5. If you have questions on that, I drew kind of like a graphic on the board for y'all last week to see what that would look like. But if you have questions, please feel free to reach out and I can help you game plan that. You can also talk with your mentor teacher. They may have a better idea of how their classroom can be set up. And so, anyways, you're going to assign the kids ahead of time. You'd have them in their partner pairs, either based on what you pick or their mentor teacher assigns them. And then you would just assign them to whatever station they were going to. And so it says you will have 3 minutes at each station. This is something we discussed that can change based on what you need for your kids. If your kids are in an advanced class and you feel like they're going to knock it out in a minute and a half, say you have a minute and a half at each station. If they're a little lower, maybe they need some additional time or some additional support, you may say 4 or 5 minutes at each station, and instead of going to all 5 stations, they may only go to 2 stations. It's okay if they do not get data for every single sample. I think when we did it in class, we actually almost ran out of time if we were doing it based on a 50 or 52-minute period. So this is where it comes to you adjusting it based on the kids that you have. This is that knowing your students part of the lesson plan and based on the schedule that you have. So I think one of our students is in a block classroom. She has an hour and a half. She should be able to fully complete, every sample, and then not everybody may be able to do all of them. So anyways, you can adjust that as needed. It says while at the station, you need to weigh each cube using the digital scale at the station, record the data in the chart, and measure each cube's volume using the ruler at the station. Record the data in the chart. I strongly suggest if you're in a lower age group, because y'all are spaced out all through sixth, seventh, and eighth grade. If you're in a sixth grade classroom, you're going to want to model what this looks like. So you may even go ahead and take sample A and not even include it in a station. Just a second, sample A is really heavy. I can't get it out. Okay, I got it up. So here's sample A. And so you may want to say, okay, first, let's remember on our scale, we need to zero it out. And so talk about zeroing it out, turning it on, making sure it zeroes out. Tell them to turn it on before they set the sample on it, because remember we discussed if they set the sample on it and then zero it out, it looks like the sample went zero. So all of those are things that you're going to need to show them. You would weigh it, and you could even have like a kid come up and weigh it. If your teacher has a hover cam, you may want to display this because not 25 kids aren't going to be able to see the scale that you're modeling this on. But if you have a hover cam in there, it's easy to be set up. You could show it and display it on the board so like everybody sees. So what would I write down? And so I can't obviously can't hold it up or you won't be able to see it. But it says 123.0 grams. And so talk about G is grams. We have that little variable noted on here. And so you would say that's going to go in the mass column. And so you would say everybody write for sample A, 123.0 grams. So it's all about the beginning stages of doing an activity. If you're very explicit with your instruction, typically you can save yourself some words later on because they've answered and they've gotten clarification. For volume, we would talk about what does this little L look like? This is length times width times height. Talk about those dots being multiplication. If you're in a sixth grade classroom, they may still use X for multiplication. And so you could just say like, hey, this will give you a head start on next year, seventh and eighth grade, we start using dots for multiplication. And so again, I would show this, I would model this. Notice it's using centimeters. This may be the same group of students that you did your reaction time lesson with. So hopefully, they remember that information you discussed about what side was centimeters, but I would have a conversation about that. I would say centimeter side says cm. I don't know if you can see it on the computer. It's the smaller side, and I would have them point at it. So anything you can get them to do so that you can clarify ahead of time is great. I would also talk about, like, okay, when I measure, am I going to start here at the end of the ruler, or am I going to start at the zero? And you would want them to start at the zero because the end of the ruler is adding space that's not being accounted for. And so you would want to tell them that. Again, if you have a hover cam, strongly suggested. You can kind of see it when I lay it on here. And so we're going to say that's 1.5. This would be 1.5, or I'm sorry, 2.5, 2.5. And then the other one is the height, which would be 2.5. And so I would even have them write it down, honestly. Like I would say 2.5 times 2.5 times 2.5 equals. And I think it's like 15.625. Let me check it really quick. This was another thing we discussed as far as if you have a lower group of students, you may want to already have the volume filled out. They will eventually realize that every cube, give or take like a little bit, because they're not perfectly cut, but every cube really should have the same volume. And so if you have a group of students who struggle, you may want to just completely bypass that phase and say, okay, all of our volumes are going to be whatever. Before you tell them, you could have them measure one cube, or you could model measuring one cube. You could have them discuss like, well, what do you notice about all these cubes? And hopefully they'd say, well, they all look like they're the same size. Well, so then what do you notice about the volume? And so anyways, you can condense that part of the activity if you need to. So I'm going to leave that up to you and your mentor teacher on that decision. But they will fill out that entire task two data table one with all of the mass and volume, and then they'll calculate density. Density is mass divided by volume. It has the little thing on here, and I would 100% let them use a calculator on this. There's no reason not to. And so I would say maybe, if depending on how much you put here, this could be 25 to 30 minutes of your activity, depending on how many you have them do. I put a built-in timer just in case you wanted to use that. And again, you can go in and change the time as needed. All right, so that's the brunt of the activity. I'll go ahead and tell you for your lesson plan, that's the explore phase. Okay, that's them tinkering and playing around and kind of starting to make connections between mass, they have a constant volume, and how that affects density. All right, task three, it says using the data collected in task two, work with your partner to organize the sample letters from lowest mass to greatest mass. Transfer the data from density from table one. And so again, I would say point at what table we're writing this on. And so they're pointing at this table. I would strongly encourage you to tell your kids to write the mass first. You're going to have some kids who try to go in here and say like, okay, well, C was the lowest, so I'm going to write C first. Well, then halfway down the list, they're going to realize H was the lowest. So I would say, look at your mass column. If you have highlighters at your school, I would even say like highlight the mass column in task two, like highlight this column. This is what we're looking at. And I would say, which one is the smallest number? That's what you're going to write first. Some groups of students, you've got to spell it out, for them to get the hang of it before you kind of let them loose. So anyways, I would have them write the mass first, have them write the corresponding density and the corresponding sample letter. This should take, I would say, maybe 5 minutes because at this point, they're literally transferring data. Okay, so there's that part. Next is the questions. And so flip to the back. This is written out for them to read as well. If you have time, I feel like it's always important for them to read the question to themselves first so that they can think about it. Remember, one of the biggest things we talk about, and you'll work on this like through all of your coursework at Athens, as far as your teach programs, is wait time. I'm just going to be honest, I struggled with that. So when you ask a question, be very intentional about giving enough time for the students to actually think about your question. If you ask a question and you wait 15 seconds, they've probably barely processed the fourth word that you said out of your mouth, and you're already telling them the answer. So again, if time allows, I would say, okay, let's flip to the back. I want you to read this question to yourself in your head, okay? And so you give them a second to read it. And then you would say, hey, do I have any volunteers if who would like to read this out loud to the class? And so then you have yet another person reading it. So they've read it to themselves, then now they're reading it to the class, or one person at least is reading it to the class. And so it says, according to the trend in data table two, in considering constant volumes, this is a great vocab word. You're going to need to clarify, what does constant mean? It means that they're the same, right? Across our samples, as mass decreases with constant volume, density does what? And so you could look here and say, so this was my lowest mass at the top, this is my highest mass. So as we got smaller, as we got closer to the top, what happened to our density? And you want them to answer that, okay? And density will get, let's see, as mass gets decreases, density should decrease as well. Okay, next we have the next little set, and you're still continuing on that back page. Again, if time allows, I would let them read it, kind of process it in their head first, and then assign it to someone or ask, if they have sticks, you could say like, okay, we're calling on Rachel, or do the random number generator, the spinny wheel, whatever you want to do here. But you would call on someone to read, and so it says, consider sample A, stainless steel. Mass over density, or I'm sorry, mass over volume is density. So this was our original sample. I did ask Mr. Vick about this because we had some discrepancies in what y'all weighed versus what he weighed. He said he noticed as he went through the sets, because he labeled these, that some of the cubes were slightly different cuts. And so if one cube is cut a little bit smaller, their mass may be a little bit less, and their volume may actually be a little bit smaller because it's a smaller cube, but it wasn't enough for us to say like, okay, every kid needs to measure every block. So this is where you would have that conversation of, human error. Human error is always something that you have to consider when you do experiments or anything related to like a human was involved in the process of making these cubes. So you would say these are not perfect cubes, okay? And so this is just based off of one of the cubes that we had. I think some of you maybe said you had like 123 or 124 or something like that. Um, I think that's what my stuff actually said 123 for this sample. So anyways, this is a great opportunity to have a brief little conversation about human error. And it says if we doubled the volume of stainless steel we're working with to this, okay, the mass would have to double as well. If density is mass divided by volume, so we have this, what's the density for a larger stainless steel cube? And so they would go to their calculator and they would type in 241.8 divided by 31.25, and they would have 7.74. You're going to need to clarify what you want them to round to because kids will ask. I would say to the hundredths place. You're also going to need to clarify, I'd bet money you're going to have kids. They're going to get, let me see what it would be. 31.2. You're going to have kids get this. And so I want you to think for just a second, how'd they get that? They use the numbers. How'd they get that? And this is one of those like student misconceptions. It's an expected misconception. They have flipped it and they did bottom divided by top. So that's something you're going to have to reiterate. But anyways, they're going to find that, oh my gosh, wow, my volume is the exact, or I'm sorry, my density is the exact same as up here. That's the whole point of this lesson as far as like from the science perspective. We want them to realize, so for a material or substance like stainless steel, which of the variables will always be the same? Density. No matter if it is a tiny cube or a large ship that was solid steel, the density is going to be the same. So that's the science perspective. Math, your perspective on this and standard is more about like data collection, analyzing variables, maybe switching around variables in a formula to isolate, stuff like that. But still, we want them to understand that that is the only variable that will stay the same regardless of the size. All right, next it says consider sample E, nylon. Mass divided by volume is density. So this is the original. Again, this might be slightly different than their sample E, and that's where we have that conversation of human error. It says if we reduce the mass from 20.4 to 10.2, having the mass, its volume would also decrease by half to 7.8125. Calculate the density. They'll go through this little process and they'll figure out, what do you know? The density is the same. So it says for a material or substance like nylon, which of the variables will always be the same? Density. And that's the end game. Next, I have this. Again, have conversation. So notice like some of them have ranges. You could discuss this range. It depends on where the wood was collected. You could talk about oak is grown in various parts of the country, the world, whatever. So depending on what geographical area it is, maybe that environment is more humid and there's more moisture in the air, or maybe it's a really dry area. And so the actual density, because the weight of the wood is going to be different, the density may vary. And you can see several items have ranges. All right. And so it says using the densities provided on the chart below, classify each element in your sample set. Some densities have ranges due to the source of the material. And that's what I just explained. And so there's nowhere on their paper to actually write this, but if you want to, you can have it like out to the side to say, okay, out to the side over here. So this is task 3, data table 2. And this is kind of an extension, by the way. This is not a required part of the activity. If you run through this activity and you've got time to spare, this would be a great extension opportunity and gives you time for extra conversation, okay, and discussion. But on data table 2, you could have them right out here beside the density. So if their lowest mass and this is not right because I have no idea what it is. Let's say it's nylon. And they're going to say the density is 1.44, but see right here, they don't have nylon written. They just have whatever letter nylon was. And then out to the side, they would write, oh, this was nylon. And so they're kind of identifying the material of the samples. The rest of this is more of the explain phase. This is where you're actually talking about the relationship, how we use the formula. How we use the formula. So it says to calculate density, we use the formula density equals mass divided by volume. You would discuss what the variables mean. So this is on here. These are vocab. This is not all that you should include on your lesson plan because, like I said, even up here, I think it was on this one of them where it says constant, that's a vocab word. Okay. So just because I put this as vocab, it doesn't mean the only vocab that you're discussing as part of this lesson. These are vocab you can discuss. We have additional practice. And so this involves them finding either density, mass, or volume given one or two of the other things. And so this is a good science application and a math application. And then that's the end of it. Okay. I didn't want to go too in depth on this discussion. This obviously could be expanded into an entire unit, especially for the biology content areas, but this is just an enrichment lesson. Remember, we're trying to make it a little bit more hands-on and just more realistic of what you would do in a day-to-day classroom. I think there's one of these, let me check, where I put the letters. I think I may have skipped over it. Here it is. So this one actually has the answers. So after they've had a chance to match them, if you have time, you can pull it up and say like, okay, check yourself. So did you get that sample E was nylon? Okay, then you measured it correctly. So it's kind of a self-checking option. Anyways, there's that. If you have any questions, feel free to reach out and I would be happy to help you. We plan to practice teach this at least 2 times in class before your assigned teach week. If you happen to teach it before then, you can reach out as well, and I'd be happy to answer questions for you. And I hope y'all are having a great spring break.